This video is for lab number 3, looking at diffraction grading laser lab. So when you first open up the web page with the simulation, you'll see several options along the top. The first thing you'll want to do is select the grading in place option, and that is going to move the grading in front of the laser on the simulation. So you'll notice now that we have a diffraction pattern that is showing up. There are a few more options that we can change above here. There is the lens to grading distance in meters, the grading lines per millimeter, so how many lines per millimeter are on our grading, and then we can change the wavelength of the laser light, and that is in nanometers. And we can go between 400 and 700 nanometers, which is the visible range of light. So in our experiment, we want to measure the second order diffraction maximum. So the central one being here, so this being the n equals 0. And then we have our first order, or the n equals 1, and then the second order, or the n equals 2. Note that the grading is symmetrical, so we do see the same pattern on both the left and the right side of the central image. And you can choose to make your measurement using either side. You can check to see that you get the same measurement, but you should get the same value. So you can just choose which side you want to take your measurements on. Now, we want to vary our wavelength in roughly 50 nanometer increments, and we want to start at 400 nanometers. So we can change the value by clicking and dragging the slider. And you'll note that when you are clicking and dragging, the smallest increment you can change is about 1.5 nanometers. But you can also make a fine adjustment. Once you've selected that slider bar with your mouse, then you can use the left and right arrow keys. So I'm pressing my left arrow key, and you can see that the wavelength is now decreasing by just 0.1 nanometers. So once you have your wavelength roughly at the value you want it to be at, then you can use your left and right arrow keys to get it exactly where you want it. And you'll also note that the simulation does actually change color according to the wavelength values. So what you'll want to do is take a reading on the scale here of the location of the second order maximum. I'm choosing to read it on the right side, but again, either side will give you the same value. So this scale here is in meters. So this will be 1 meter, this will be 2 meters, and the scale is further divided into 10 subdivisions, so 0.1 meter divisions. And you'll want to consider the size of those divisions as part of your reading uncertainty. And you'll notice that the maxima, or the bright spot itself, has a bit of width to it. So you should also consider how wide the dot is and how you're going to estimate exactly where the center of the dot is located when you're recording your measurement. So reading this value on the scale will give you the W value, which is in the equation that allows you to determine the sine theta value. And then the L value comes from the lens to grading distance. And we're going to keep that constant at 10 meters. Now, for the W value, because we're reading on a scale, you'll want to consider reading uncertainty and potentially the width of the dot, as I mentioned. For the values that are above on these sliders, we can still consider the size of the smallest division. So with our wavelength, because our smallest division is 0.1 nanometers, generally you can use half of the smallest division. And if we click over to the grading lines per millimeter, so I've clicked on this scale, now I've selected it, and again, I can use my left and right arrow keys. So pressing the left and right arrow keys shows me that the smallest division on the grading lines per millimeter scale is 1 millimeter. So because that is the smallest division there, you can again use half of the smallest division. And then finally, to determine the smallest division on the lens to grading scale, I'm going to select it with the mouse and then just use the left arrow key. So you can see that the smallest division on that scale is 0.01. So again, using the left and right arrow keys, I can determine what the smallest division on that scale is, and it's generally appropriate to use half of the smallest division when we have a scale like this. So once you've measured the value of W for your wavelength, then you'll want to increase it by roughly 50 nanometers. So I can slide the scale up, get it roughly around 450, and then I can use my right arrow key to do the fine adjustment to get it to 450, and I'll repeat those measurements in increments of 50 nanometers all the way up until the 700 nanometer wavelength. And that covers the data collection portion of this experiment.
So now I'd like to talk about how we're going to graphically verify our grading equation in this experiment. So we have our equation 1, which says that d sine theta is n times lambda. And we want to plot a linear graph with our variables. And in this case, our variables are the wavelength lambda and the angle of the second order maximum. So that would be sine theta in this equation. And because the wavelength is our independent variable, I line that up where the x variable would go and rearranged equation 1 to compare it with the equation of a line. So we have y is equal to mx plus b. So our prediction for this lab is that if we were to plot wavelength on the x-axis and sine theta on the y-axis, that should give us a linear graph. And that'll give us a constant value for the slope where we have n over d, n being the order of maximum, so n equals 2 for all of your measurements, and then d being the diffraction grading spacing, which we want to determine experimentally. So our predicted slope value is equal to n divided by d, and then our predicted y-intercept is equal to 0. Now, with our measurements, we're not actually able to measure sine theta or theta directly, but we can use trigonometry and the geometry of our setup to get a second equation for sine theta. So using equation number 2, we have sine theta is equal to W divided by the square root of L squared plus W squared. So using your measured values for W and for L, so W being the measurement from the central image to your second order grading, and L being the distance from the lens to the grading. So if you find it helpful, you may want to write a substitution. Since we are plotting this on the y-axis, we can just say that this is equal to y. Then when it comes time to determine the uncertainty for what you're plotting on the y-axis, then we know that if we write this substitution, that the uncertainty of sine theta is going to be the same as the uncertainty of this whole thing. So w divided by square root L squared plus W squared. That's the same thing as uncertainty of Y. So if you find it less confusing, you could write a substitution and say that Y equals this and use that to find the uncertainty of Y. Also note that you never actually have to calculate theta. So when you're finding the uncertainty for Y, it's going to depend on two variables, L and W. So that means we're going to write our calculus formula. So we'd have a partial derivative of y with respect to w squared times uncertainty of w squared plus partial derivative of y with respect to L squared times uncertainty of L squared. And then this whole expression is also square rooted. So when you're taking these derivatives, you will have to keep in mind that particularly with w, that you have a w on the numerator and the denominator, and you've got a square root and some squareds going on. So you'll have to use some combination of chain rule and the multiplication division rule, or whatever your rule of choice is to determine the partial derivatives to go into your uncertainty propagation equation. Once you've plotted your graph, so you can plot the graph using line graph. So you'll have your graph of our y variable plotted versus the wavelength. We expect to get a straight line graph where the y-intercept is 0, and the slope of our graph will give us our value of n divided by d. So using the value of the slope, so m and its uncertainty from line graph, we can set that equal to n over d, and then we can solve experimentally for our value of d as well as its uncertainty.